theorem says that a of n, where we understand that in our case, let's look at it like this, that a of n is where n is a prime number, and we have to see that this is a theorem, right? And we assume that our language is context free. It is context free, okay? Therefore it must satisfy the pumping lemma for context free languages, and let j be the pumping length guaranteed by the lemma. So step 1 would be that we select a string where p belongs to the language such that its length is a pumping number, is a prime number n. Where n is bigger than or equal to the j. So this j is something that we don't know. J is something that he decides. We don't decide it. But let p be equal to a to the power n, where we know n is the prime number. And why we do that? Why we say this? Because if he says, oh wait a minute, I want to say that j is equal to 4, we say it's bigger or equal to n, where n is a prime number. It needs to be a prime number. So if it's not a prime number, the next bigger prime number is 5. So it will become that. Why? Because we put that n on this, and p is our new length. And just like we said that the length of p is bigger, this is true. So the j was, yeah, this is what I said. It would be more accurate to say it like this. Now this is a step 1. The step 2 is, according to the lemma, the opponent splits the string into 5 substring. For example, p is equal to u, v, w, x, and y, such that they satisfy the following structure constraints, where v, w, x, the length of these is less than equal to the j that he decided, and v and x, the length of this is equal to r greater than equal to 1. We know that these two will get pumped. When these two will get pumped, these are all the two things that will get pumped. And in these two, which will get pumped, we know that these, we can give it a new variable, r for example, which will be added to the original length of the string. In that way, we will keep track of the variables that got pumped. For example, u, v, w, x, y. This is our original, like, proper string. And these are the two that will get pumped. So the length of these, we can say, is r. That way, we will know that if we take r and the remaining of the word, which is w, y, and u, we basically have the whole word. It's the same thing. This is the same thing. Now, once we did that, we can then say, okay, the pumping section v and x combined cannot be empty. This holds. Now, step 3 is, we choose the pumping exponent to be I equals to n plus 1, where we forced the n to be a prime number. And according to the pumping lemma, the resulting string is p. The new length would be u, v, whatever he chose, n plus 1. This is what we are doing. And why are we doing it? I will tell you. We're saying x to the power n plus 1 again, and y. Now this is our new this is a real prime number. We know this is like a real prime number, and it also belongs to the language. It belongs to the language because we made it that way. We made sure that this n of ours, just like I said before, is something that is a prime number because we put it on here. And because we only get to choose n, we only get to choose this could also be our I in generally, but we can look at it like this, that n plus 1, this is the thing that gets pumped. So we decided it to be this way, that whatever is getting pumped is +1 to it. So I is generally getting pumped, but we're doing +1 to this. Now what that means is that once we do it, we might say step 4, which is algebraic derivation. So the length P is actually equal to U plus I multiplied by V length plus W length. Oh, or maybe let's try to write it in a way that it gets all the way to this side, so I can write it completely, where plus I multiplied by X length plus Y length. So this would be the new length, because we know that we're multiplying I. This is the pump situation, that we only pump these two variables. We know that we pump it. Whatever the length of I is, we sometimes say I equals to 2. Then we pump it 2 times. We pump the V 2 times. If I was 3, we pump it 3 times. It is a general rule that we always do follow. In that way, we can also say that the length of P, the new length of P, would be U plus V plus W plus X, the length of X, plus Y plus the length of Y, plus I minus 1 V, length of V, plus length of X. Now see what happened here. This is our original situation. If we plug now, let's try to understand this like visually. Okay, what's happening is, so let's look at our string, right? You say P is equal to U V W X Y, and the original length is that is length of U plus length of V plus length of W plus length of X plus length of Y, right? When you choose a pumping exponent like I equals to 3, you're telling the string that repeat V and X sections so they appear exactly 3 times. Let's write it down like physically. So the new P would be U plus V 2 3 plus W plus 1 2 3, when I is 3 times, plus Y. Let's look at the length of this new string. You're literally multiplying the length of V by 3 and the length of X by 3. So the new length would be, you can say U plus 3V plus W plus 3X plus Y. Now we write it with I minus 1. Why? Because you can calculate the total length by doing exactly what we did above, but just by multiplying by I directly. But in mathematics, we rewrite it using I minus 1, because it separates the original situation from the new we just added. Think about it this way, that out of 3 copies of Vx, one copy was already there at the beginning. You only actually added 2 new copies. Let's rearrange the letters of our pumped strings and group them together, original pieces. What we get is, we get p to the power u plus v plus w plus x plus y, and that gets plussed with v plus v plus x plus x. These are extra. These are our extra. Now let's write out the length of those. The length of original is n. The extra piece is 2 copies of v and 2 copies of x. We can write as 2 multiplied by, multiply by length of v plus length of x. Now where did the 2 come from? It is our original exponent minus the original copy. So 2 is 3 minus 1, right? That's 2. And this 3 is our original I. And if I say 2 is equal to I, we get one step back. And we know that we minus I from 1 times, or the pumping times, we minus it 1 from it, then we get back to the position where it was not pumped. And we can write it this way, that u plus v plus w plus x plus y, going to get plus with I minus 1. This is extra added length. Then v, length of v plus length of x. And the new length becomes n plus I minus 1 times r. And we know r is this is r, we can write it like r. And this is our original length, remember? And this is derived from the fact that this, like one step back, we go one step back. And we can say that this is a general formula, that n is the original length minus a plus. If you plus this, then we basically are going one step back and doing the same thing. And r is this is the new total length. We can understand this because it sets a perfect trap that in this way we can plug I equals to n plus 1. And when we say, okay, I was n plus 1, I is n plus 1, we can plug it back in. And see, we can put the value of, like, we chose I n plus 1. Remember, that's what we did when we did the decomposition. U v w x y, we said this is n plus 1. That's why we did it, so that we can put this back here. And when we this is the same as it is n plus n is this is n, and n plus I minus 1, and this is r. And the moment we say that, we put n, we plug it back, we plug it n plus 1 back in I, we say n plus 1 minus 1, and we say r. We can say that this basically crosses out. It's like, you can cut it, you can cut this thing, and we're left with n plus, because plus minus 0, n plus n multiplied by r. And we can then factor it. Once we factor this, we get n from this term, we get 1 plus r. This is the perfect formula we get that can help us understand. Now we can go one step back and look at our original formula, or what we were doing back then. Continuing our solution, we understand that this is where it was coming from. Now we substitute this length, and we say that length, it becomes n plus, just like I said, n plus 1, and this becomes 0. This step we already factored out. But then we know, just like I said, then we know that after creating this formula, we know that in step 5 we can just, it belongs to the language and then it can be factored. We choose our initial length such that n is bigger than j and j is bigger than 1. Since we easily pick an initial prime larger than 1 and then we factored it, because plussing doesn't give us that, multiplication does. Then we know that therefore 1 plus r is bigger than 2. For example, we know that v and x together is the law that it's r and is bigger than equal to 1, and based on that 1 plus r is bigger than 2 because you added two terms together. You add something with 1 and r is always at least 1, and that's 2, and n is our decided string, and our main goal was to multiply two numbers together. When you multiply two numbers that are at least someone is bigger than 1, then you always get a composite number. And because the length of that prime is the product of two integer factors and are strictly greater than 1, the length of the pumped string is guaranteed to be a composite number. And a string with a composite number of a's cannot belong to language. This directly contradicts the pumping lemma assertion. Thus our initial assumption is false and the language is not context free.